Right, sorry for the long title, but this is going to be a report on some joint work, partially in progress. With Alberto Canonaco and anõ�ne. So the project has two parts. So the first part, which is essentially the central part of my talk today, should be soonish. But the second part, which I try to explain, requires more work, and so that's the real part, which is heavily in progress. Okay, so I'll start from some motivation. And so the motivation is actually this theorem, which is used Rickard. It goes back, I think, to 1989, something like this. So actually, the theorem was brought to my attention some years ago by Inich while I was giving a talk about the uniqueness of enhancements. And at the moment, I didn't quite understand, how relevant it was for my work. But later, actually, recently, while trying to, understand better the theory of weakly approximable triangulated category by Arnold, actually it came really clear to my mind. So the situation is the following. So we are really in the sort of, so to speak, affine situation. So let's consider the following. So now we start listing some conditions regarding the existence of equivalencies involving all, relevant triangulated categories associated to this ring. So the first one is that, we require these two categories are actually equivalent, and then you start adding decorations to these categories. So you continue with, so you look at, so this is actually the unbounded derived category. So you can add bounds to the complexes. So you can look at those that are bounded above, those that are bounded below. Those that are bounded in general. So. And then you can, you can actually specialize a little bit more. And so you can look at actually 3 more categories in the list at the moment. So you can look at the bounded above homotopy category. Finally generated projective modules over the two. And then you can, sorry, I want to squeeze everything in this board. So and then you can look at those that are bounded above but with bounded cohomology. And finally, sorry, is this visible? Okay, so this is an incarnation of what we usually call perfect complexity.
The last one you mean the last one you mean as projective formula.
Yeah. Sorry? Oh, as projective. Right, so you have a bunch of conditions involving all the relevant categories associated to the two rings, and then you can start asking yourself which are the implications between these two conditions. And the situation is as follows. Then, yeah, actually, this one, it was first condition is not in the original paper by Rickard, but it's easy to actually make use of this other conditions. So you can start looking at all these 6. So, and the theorem says that all these essentially equivalent. So, and also this one is equivalent. Then you have this detour. So these two are equivalent, and this one is the other one. Okay, so that's in general. And so the additional condition is that if you assume if R is, say, left coherent, for example, Ethereum, then 0 to 6 are equivalent.
Sorry, another simulation is fine. Is it K, there's a minus B?
Yeah, sure. So these are when when you see this decoration, so minus and B, I mean really complexes which are bounded as complexes. And the B, the comma B, means that the cohomology is also bounded below 1. Yeah, sorry. I briefly mentioned. That's a good question. Yeah. So these are really complexes which are bounded above. So some point, a bunch of zeros, and those that are bounded above and below, and those that can be in one direction, but the cohomology is bound. So that's a condition. Yeah. And so this is the theorem, right, that goes under the name of Morita theory for derived categories. And yeah, I think definition thing. So if one of the 6 conditions holds, say when R is coherent, then we say that R and S are derived. And we don't really need, the key point of Rickard's theorem is that we don't really need to worry about which category we want to be involved in the definition of being derived. And so, yeah, so let me come to the question. So why we care? So that I think, the theorem is beautiful in itself, but so I should also ask myself why we got interested in this and why, with approximable triangulated categories and DG categories are involved in this picture. So yeah, so my claim is that the theorem can be looked at as a sequence of implications. So some of them are going downwards and some of them are going upwards. So let's look at the downwards. So why do we care about downward implications? So the first observation is that so they are related to the following, so to speak, classical question, which is as follows. So you can take the derived category of a ring, and so you can start asking yourself, so how intrinsic is, and then you have 2 choices. So my claim is that if you stop at 3, so you can look at the T structure. R, and this is all about essentially the implications that goes from and the relation between them. So and then you can start asking how intrinsic are the other subcategories, which are more complicated, more intricated. also which let me write like this. So question mark. Okay, so I can add all the decorations that we want. And this is all about the relation between condition 1, 2, 3, and now, I mean, they do imply the remaining ones. So in other words, it's all about understanding how the structure, or let's say, I mean, the equivalence class of the structure is preserved under equivalences for the first implications, and how can I deduce that these categories are so much intrinsic that they are preserved under equivalences of one of the bigger categories upstairs. Okay? And so that you have to
all statements about the category of quasi-coherent, not coherent.
Sorry.
All the statement is about the quasi-coherent shifts, but not coherent shifts, right? In this sense.
So no, wait. So up to here we are dealing with the quasi-coherent, and then when we move down here, so these are coherent, right? Because so in particular, so in this situation you can look at the one of any of these guys. Say this guy here, approach is nothing but so remember that being coherent means that any finite generated idea is yeah, so this is just DB. We don't know. So it's really about coherence. So that's the difficulty of the problem. Actually. So how did you cut out these much smaller categories out of a big one? Okay, so that's so that's the content of this classical question. Okay, that Rickard solved essentially in the so to speak advanced stage. And the second reason why we care about essentially the downwards implications is that essentially if you go so downwards it means also that you take this turn a little bit. So it means that if you look at now, which was the implication, 6 implies 5, which my convention is a downward implication. Right. so I mean the proof of this, the original proof contains a gap. So this was brought by Henning-Krause a few years ago, and so noted is I think around 2017, something like this. So yeah, that was a sort of beginning of the story together with Anon. So they started working very hard on this notion of metrics on triangulated category, and after all, on the notion of approximable. So there's a way to find a repair for this such a missing information. Okay, so right, so the implications downwards are all about the fact that some additional structures that could be T structures or I mean this small category can be intrinsic or not inside the big category. And what about the upwards implications? So at least in the coherent case, where you can really go back, yeah, say coherent. Yeah. So yeah, it's all about they are all related. The following. So, question 2. So let me me write in a naive way and then comment shortly. So the situation is the following. So let me write in a very abstract way. So that S and T be triangulated category, which are generated by their compact objects. So say TC and LC. So remember that an object is compact if on from an object to a coproduct of objects inside the category. I mean, such that it's a natural equivalent to. Oh, it's not readable, Daniel.
No, fine.
So so as I said, so an object is compact in a triangulated category set if on from the object to a coproduct is the same as taking the coproducts of the ons from the object to the simple objects. Okay, so the question is, so we start in the situation and let say F between TC and SC be an exact equivalence. And the question is under which assumptions it lifts to say F twiddle from the big categories. So it's not hard to see that this is indeed the key point, right? Because you assume you want to show that all these are equivalent. So if you are able to deal with the, question 1, then you go down from 0 to 6, and then you end up to a category which consists of the category of compact objects in the big category, right? So you have an equivalence between perf R and perf S, and if you are able to answer in the positive to the question, then you can go back to the big category. Okay, and so you get this circle of implications. Okay. So, of course, let me comment a little bit on question 2 for a second. Let me try to explain why we should expect some relation. So, I guess that you understood that for the downwards implication, there is a close relation to with the theory of approximable triangulated categories, essentially because they originated from actually the tentative to solve one of the gaps in these downward implications. And now I want to explain why G categories and uniqueness of the G enhancements are relevant for the outwards implications.
So can I just ask a quick question about your definition of derived equivalent? If R is coherent and R and S are derived equivalent, is S coherent?
So you're asking if being a coherent is a derived invariant condition. So that's your question.
Yeah.
This I'm not sure. I don't know actually.
It's potentially a little asymmetric that you assume R.
Yeah. It's a good question actually. So for example, you could ask even a more naive question, which I think is open actually. So is being Noetherian a derived?
I've asked someone no one could answer.
So yes, so you can add me to the list of people. So, but it's a very nice question.
Can you say very briefly what the gap is in the proof?
Pardon me?
What is the gap in the proof that having noticed roughly?
Yeah, essentially the point is that so he's implicitly assuming that so it's a technical passage in the proof, which doesn't quite make sense. So it's a really technical issue. So, but I think my impression is that somehow Rickard really wanted to refine a little bit the answer to question 2, but didn't quite make it. Okay, so it's really a technical passage. So because you see, so the point is that the relation between assume that everything is coherent for simplicity or even Noetherian. So the passage between d little mod r and curve R is quite delicate in both directions. So in both directions. So
So the gap is not for like finite dimensional algebras or like reasonable algebras, it's for like rings that are horrific. Or...
no, okay, so of course there's no counterexample because the result turns out to be true. So okay, so the key point is that the line of arguments is incorrect or not quite correct. Let me put it like this. So the result is correct. I mean the theorem that I stated is proven. Actually, so as a consequence of our result, we get yet another proof of this theorem. But so there is no counterexample. So yeah. So more questions? Okay, so let me go back, a quick comment. So about question 2. So of course it has, we know very well that it has a positive answer. In at least 2 cases. So of course the first one is so it's very geometric, but not that the other one is not. So you have to assume that D and S are nothing but D cubical x1, D cubical x2, xi small projective over a field, right? And then everything boils down to the theory of Fourier-Mukai functors. So if f from TC, which is just in this case dB, so S1 is an equivalence, C.
You mean D per? Not dB per?
I'm assuming it's full projective, so it's really the same.
Oh, okay. Right. Okay. Yeah.
Yeah, okay, you can refine also to non-smooth cases. Let's content about the easiest possible situation. Then, so we know by beautiful result as well that f is a Fourier-Mukai functor. And then we're in business. Then f extends to equivalence. Okay, so yeah. So the second case, where so somehow let me put like this, so slightly more general. So is when E and S are great, meaning that have a DG model. So T is the amount of the category of some DG category, pre-triangulated DG category C1, and S. Actually, write an equivalence here, and I should also keep track of the equivalence. Looping C1 and C2. Right, and so you start with F, that now you can think of an equivalence between C1 and C, so that are means the full subcategory consisting of compact objects in C1, and then you do the same with C2, and assume we know that F can be lifted. I'll try to explain what it means in a second. So say F, C1, C1, 2C, and then sure, I should explain what's the error here carefully, right? So then we know by working, it's a classical thing. So I think it's well known by Russian school essentially. So that it's of course contained in the work of Drinfeld and also Keller. So we know that actually whenever you are in such a situation, so you can actually lift your equivalence between the subcategory consisting of compact objects, then you get this so F twiddle between C1 and C2 such that so if you look at F twiddle, this is indeed an equivalence between X and 2. Okay? So in other words, if you know that actually your triangulated categories can be lifted to a higher categorical model, and you also know that also the equivalence can be lifted in an appropriate sense, then you are in business. Of course, yeah. The mod R. Sorry. So we are always assuming that these guys are company generated. So that's exactly. And yeah, then you are in business, and of course the mod R, or you can start taking any decoration you like. You can take a quasi-compact, quasi-separated scheme X. You can look at a closed scheme, look at a complement with quasi-compact. Then it also has a G enhancement, right? And of course, you need to make sure that this assumption is verified. Okay? So
the assumption there is just the F lifts to a constant, not the equivalence.
So what? The key point.
J should be an equivalent or just a constant?
So it's a little bit, first of all. No, the point is that so if you give me a triangulated exact equivalence, then in general it's not clear if it lifts or not. Not just to a functor, but to a quasi-functor. So it's a problem. So the slogan. So the uniqueness of enhancements for, say, T, which is algebraic, of course, implies upwards implications.
I didn't quite get the conclusion.
Yeah,
the assumption is that little f induces an equivalence on aeigenor.
If you wait 5 minutes, I try to make the statement precise, I would say. Right. So the key point is that how do you make this precise? So you want to lift. So you take HQV, which is by definition, you take EG cut, and you localize the quasi-equivalences. Okay, so this is one way to see the localization. So it's the homotopy category of the category of EG categories with the appropriate model category structure. So let's work it out. So what is a quasi-equivalence? So it's a functor, G functor F from C1 to C2. Such that so first of all, so it induces a quasi-iso of complexes from any object AD, C1, and then you look at the quasi-iso on C2. So C, and now the same way you can take the homotopy category of the G category, you can take also H0 of F, and you are answering this is essentially super. So you have a bunch of these special functors, and you formally invert them, and you get HUE, and this is the place where you actually want to leave your equivalence. Then let me take a look to the results. So we say that an algebraic triangulated category, T, algebraic just means that it means the H0 of some DG category C has a unique enhancement. Given a triangulated category, say D, and an exact equivalence say F from H0C, H0D, there is F, a morphism in such a localization from C to D, H0 of F is an equivalence. Okay, and now I guess you understand. So in general, I mean, the lift is not a functor, it's a zigzag of functors, and if you assume that, I mean, you have a, modified abstraction of DG it's just one roof, I mean, representing F, so it's not really a functor, it's a roof. And now you see what I mean, right? So if I know that, for example, so in our case, knowing that R have a unique enhancement, provides the implication from 6 to 0. So we can really go back, right? Because you start with an equivalence between perf R and perf S, you know that this can be lifted to by uniqueness of enhancements, which is by now a theorem actually, so I'll come to this later. So if you can lift this to morphism in HUE, then by the Greenfeld-Keller trick, it leads also to a functor between the big categories, or they are essentially the.
So are you stating that H0 small f is capital F? Or just
No. No. So you are touching a delicate point. So it's not required. So if this happens, which is by now, so for example, it's known in the smooth case, then that there it can be done. So you can really lift the given equivalence. So here I'm just saying that you can lift given an equivalent. There exists one that can be lifted. Okay. And so, for example, it's a very nice and I would say widely open problem to understand whether the enhancement of perf R, so the easiest possible case, is strongly unique in this sense. So if you give me an equivalence between perf R and perf S, so can I really lift this precise equivalence to something in HQE. Okay? So what you can prove is that you can lift to a factor which behaves in the same way on objects, but you cannot control models. So it's a very interesting problem. I think the expectation is in general that the answer should be no in the affine situation. So you would expect it. The name. Okay, so right. So I hope I clarified a little bit the different natures of the implications. So downwards is a problem related to the intrinsic, the fact that some subcategories are intrinsic, and the direction upwards, it's all about lifting equivalences. So in my viewpoint, which is of course not the only possible one, it's all about the problem of lifting exact equivalences to something that live at a higher categorical level. So that's the the twofold nature of the theorem. And of course in modern language, right? Because the way that Rickard went from perf to dv mod R, it's more like in the spirit of the geometric case which is on the board. So it's essentially constructs a tilting complex, right? So it's sort of a Fourier kind of element. So it's not really in the language of G categories. Okay, so right, questions? Okay, so right, so let me state our results. So the situation is the following. So let me start from actually. So the geometric application. So we like so much. So we start with xi I equal 1 and 2 be a quasi-compact, quasi-separated scheme. So yeah, and let that I in X I be a closed, ballistic closed subset such that the complement is quasi-compact. So if you want to simplify your life, just assume that Zi is equal to Xi and the result is interesting anyway. So actually it's complete in that case. So you don't need to wait for the second part of our project to answer. And then consider the statements. Okay, somehow I have to take a little bit of time to write down the same list of equivalences that were mentioned in Rickard's theorem, but now in the geometric setting. So for some reason now it's start from 1 and not from 0. But anyway, so again, you can start from the big category of unbounded quasi-coherent sheaves with support on Zi. And then again, you can start adding decorations. So anyway, so space over here, and so 4, so bounded quasi-coherent support Z. Five. Okay. So now we have to find a replacement for the weird categories that appear in the second part of the list. So there was a K minus of finely generated projective modules, and this is what is usually not like. That's not a standard notation, but there are pseudo-coherent complexes. Now, yeah, maybe it's not worth giving the definition. So I'll tell you some special relevant case. Not me. One second, and then explain my notation. So, and 7, I think the compact objects in the group category. Okay, so what are the perfect complexes? Are essentially those that are approximated in the nicest possible way by perfect complexes. So it's essentially a complex that sits in a distinguished triangle. So the first piece is a perfect complex, and the second one has cohomologies that can live in arbitrary negative degree. So of course it's a and waving. So assume, for example, so that they are what they are. I mean, they're usually called complexes approximated by compact objects. And the example, so if you take xi material, so then you get back the usual thing. So it's really D minus of complexes with coherent cohomology, right? And this one a priori is just the intersection of this guy with DB, right? So that's the definition of this guy. So this is just pseudo-coherent complexes which are bound with cohomology. So, and of course, in the Noetherian case, you get back the usual DB code. Okay? Right, so you have this bunch of, classical triangulated categories. So say that there's xi, zi, and of course you want something relating the various So then, of course, you would expect that, the downwards implication are always true. So no assumptions, right? And now, of course, you would expect, so that's going to be the second part of the project. So we would expect that also the other implications hold without assumptions. So, and if you somehow follow my tentative explanation of the nature of the implication supports, so it's all about showing that the category of perfect complex is supported on a closed scheme the unique enhancement. Okay, so that's the key one, which is a little bit embarrassing that this result cannot be deduced by what we already proved, but it's like this. And then furthermore, so the state of the art is the following: if either so xi is equal to zi, so there is essentially no condition on the support, or xi is Noetherian, then 1 up to 7 are equivalent, are all equivalent. Plus, I should also mention, of course, Rickard is not exactly in this setting, right? So because we are not assuming that the ring is commutative. So, but anyway, so with plus we recover completely. Okay, so before explaining a little bit, a few details from, which is the key idea in the, the proof of these implications and then the way back. So let me displaying some consequences. Yeah.
And what about int core?
So yeah, so in the, I mean, you mean so that's what you mean if I your multiple category. So you want the in the so let me remove the. That's what you mean. Your multiple category of sorry in the code. So
The incompletion of.
yeah, and you look. So then, when you take the incompletion of core, so the standard thing is to take injectives and then you multiple category of injectives. So I think in Jacob Lurie's notations, this is what goes under the name of unseparated derived category. Yeah, whatever. So yeah, I understand. So we can also prove this one. Okay. So you can also add list add this to the list.
And how do we get to the list? So,
They are all. I mean, okay. So if you assume so, the implication is that from the fact that you get an equivalence between dB co, or well, at least assume that xi coherent, okay, or Newtonian if you want. Okay. Then well, it's easy to understand because so for example, if it's if in the sorry, I made a mess. So if you assume, for example, there is Newtonian, the scheme is Newtonian, then you know that the compact objects in this category here, they are precisely dB co. So essentially, then you can easily guess how to deduce the result about the unseparated derived category from the result about the dB co. Okay.
now this is about the up interpretation, right? And what about the downward interpretation?
So if you know, I mean, if you have an equivalence between dB co, this implies the existence of an equivalence, but it's equivalent to having, it's indeed equivalent to having an equivalence between dB co and dB co, right? Because it's the argument as before. So they keep on.
I mean, you mentioned that an equivalence between this int core. We need to use the equivalence between usual.
Sure, because that's the claim, right? So the compact objects are dB co. So yeah, that was my. Yes, you can easily add this one, but I didn't want to introduce the notation, so yeah, if you want. So actually, it's related to one of somehow your question is related to one of these consequences that I want to explain. So first of all, yeah, the point is that the derived category of singularity on X, so X quasi-compact, quasi-separated, and then of course, I mean, so if you want to add the additional decoration about the support, you have to be a little bit careful because at the moment you probably need to assume that X is Newtonian, but probably in the long run it will be true anyway. So is a derived invariant. Take two schema X1 and X2. So and assume that they are derived equivalent in any of these equivalent senses. Okay, then the derived category singularities are actually equivalent. Second thing is that being regular is a derived invariant, which is very much related to the derived invariant for Newtonian schemes. Okay, and maybe the third one. Okay, so you can look at to the stable category. Which is actually a fancy way to look at acyclic complexes. Of injective models. It's also important. Okay, And of course, you would expect this to be true with the additional operation concerning the support. Okay, so let me move to section 3. Ideas from the proof. So as I mentioned, actually, so essentially the theorem, as for Rickard's theorem, is just an excuse to understand better, I mean, how intrinsic are given subcategories in one direction, and how feasible is to prove that the category of compact objects in special cases have a unique enhancement. And so let's look again at the downwards implication. So yeah, so the point is that, so definition, so let D be a triangulated category in coproducts. So that's a definition by Unknown, actually. The brand new theory that he invented recently. So with coproducts, then D is weakly approximable if so there exists so a compact generator, G a compact generator on D. So G is the smallest full subcategory of itself. It contains G, all coproducts of G, shifts, and okay, so a positive integer, so a positive integer, and a T structure. Well, so D equal to 0, D equal to 0 on T, such that. So now we come to the technical implications. So we want the generator to be bounded above in a prescribed way, vanishing of ohms. So yeah, such that the first condition is that G, as I said, has to have bounded cohomology in a prescribed way. So A bounds the cohomology of G, and then you want a cohm between G and D more or equal than minus A is 0, and so now we come to the weird condition. So that means, I mean, that gives sense to the notion of approximation. So for any D, let's say F, I'm sorry, D is more or equal than 0, there is an exact triangle. So say, so E goes to F, goes to D. So where this guy here is contained, so I'll write the condition and then I'll explain. So E is actually generated by G undertaking arbitrary coproducts, shifts containing this interval, and direct summands. Okay? And this guy has a smaller cohomology, so it's a 1 less D cohomology. Okay? So that's the reason why they are called weakly approximable, because you take an object in this smaller or equal than 0, anyway, bounded above, and you can approximate the object, at least the first non-trivial cohomology of the object, by G and its coproducts. So that's the condition. Okay? So examples. So D mod R. So this is really an exercise. So you can take G equal to R and A equal to, I think, 1. But also DQ co ZX. So this is an exercise. So this is a deep result by Hammond. So they are weakly approximable. So, okay, so the slogan is that a weakly approximable triangulated category is a category which is generated by an object, and the generator and the T structure they nicely match. Okay, and yeah, so but if D is weakly approximable, then we can define the following categories. So yeah, you can define D minus. So by using the T structure, you can define D plus. You can find D just using the structure, right? And of course, you can define DC. You can look at the compact objects inside this category, and then, of course, I mean, you can repeat the notion of approximation by compact objects also in this setting, and you can look at also at DBC, which is Z minus C. Okay, and so it's easy to guess in these two examples, which are over here. So which are the categories? So they are essentially the categories which appear in Rickard's theorem and in our result. And the theorem, actually, I have to say the main theorem, even though it comes after the geometric application, is the following. So let D be weakly approximate with approximate triangulated category. Consider diagram of inclusions. So D plus, D minus, D plus, and then you get D minus C. So which contained here, it's contained here, it's contained here. This guy is contained here, contained here, like this. Then you get DBC, and you can look at compact objects, which are in our setting always bounded above, okay? But not necessarily bounded below, so you can look at DCB, so it's DC intersected with C, okay? So this is included here. So this is a dotted arrow, and then there's also a natural inclusion in this one. I'm done. Can I just take 1 more minute to finish the statement? Is this okay? Okay, thanks. Then all the inclusions apart from the dotted one are intrinsic, And furthermore, if so first condition D is coherent, so which is a weird definition of coherence for a triangulated category, which essentially, in the two examples, boils down to the requirement that R is a Noetherian, X is a Noetherian. So the examples are Noetherian or X Noetherian. So you want that DC is containing DBC, so which is not automatic, and if D is an object in D minus C, is such that so it's a technical condition anyway, such that you can look at the right orthogonal to D, and this contains the whole DBC, then D is equal to 0. So if one of the two conditions is satisfied, then also the dotted one. Is intrinsic. So in other words, this is a very general result that implies in particular all the downwards implication in our theorem. And finally, upwards. So it's about uniqueness of enhancements. So we know by the work of Lunds and Love, so that F R and the unique enhancement. So this gives back the upwards implication in the Rickard theorem, and then we prove that so a special case of a model, theorem of a few years ago by the three of us, says that the X quasi-compact and quasi-separated, then perf X as a unique enhancement. So this deals with a case where we don't have support in the upwards implications, and so the theorem, which is work in progress, is that perf by the three of us, so that's really in progress, that also perf Z as a unique enhancement. So that's really something we are really working on. And it's very embarrassing that, so while this result by Lunds and Orlov is very easy to prove, it's much simpler than, of course, the result about schemes. So in the supporting case, also the affine case is really clear. So sorry, I was moving on time, so thank you for your attention.